All right. One more example here. Searching a single array for duplicate numbers, and you could pretty much do the same algorithm we had here and just pass in the same array for array 1 and array 2, and it would find out if array 1 has any numbers in common with array 1. But let's do something a little more interesting and have something that's not linear or quadratic, so that we can see how we do proofs with other types of orders of n in them. So I'm not going to be as nice with colors here, but we'll say function find duplicate. And again, we're not going to worry about returning the duplicate. We're just going to say whether or not there is a duplicate, one number that's duplicated in an array. And it doesn't have to be a number, actually. Anything in the array. Alright, so the first thing we're going to do with our array here is, well, like I said, we could do the quadratic solution and compare every number to every other number, which is a really naive solution. The one we're doing here is fairly naive too, meaning it's not optimal. But let's do something a little bit better, something in between the optimal solution of using a hash table and something really bad, like doing nested for loops. So instead, we'll take our array and we'll first sort it. So we'll say that array is equal to, I don't know, merge sort on our array. So let's say we sorted the array. Now we'll loop through and we'll say for I n, and let's say we're going to start at index 1. This is going to be base 0 index, all the way up to array.length. So we're going to loop over the indices of the array, and we're going to say if array at I minus 1 is equal to array at I. We found a duplicate, so we'll just return true. Otherwise, we'll return false. There are no duplicates. Alright, so how does this work? Well, if we sort the array, that means that any numbers that are the same will be right next to each other in the array. And what are we doing on this line here is we're saying if the number to the left of the current number is the same as the current number, then, well, those are duplicates. And there's no way to have duplicates that aren't right next to each other somewhere in the array. Alright, so what's our total running time of this function? Well, we've got our merge sort, and merge sort, I believe we came up with in the last class was 21 n log n plus 21 n. I think that's about what we came up with. So we have 21 n log n plus 21 n. And now we have, let's just count up our operations. This one's going to be a little bit trickier, so let's say we have 1 times n operations here. And we have, let's see, a bracket here, double equals here, and a bracket here. So let's say we're doing like 3n here. And then we've got our plus 1 for doing some sort of return, whether that's a return true or return false. And, you know, I'm sort of leaving myself some wiggle room here in that this is probably more than just 1 n amount of work. At the very least, it's 1 n plus 1, but I'm not going to worry about the plus 1 for doing the condition check one more time than the body of the loop. Just trying to get you comfortable with sort of ignoring some of the unnecessary details to some degree. So like on an exam or an assignment, if you're plus or minus an n and plus or minus an n log n and plus or minus your constant term, you're going to get full credit. I'm not too worried about you getting it exactly correct according to my sort of pseudocoding class rules, since each person you see teach this content will be a little bit different on how picky they are. Alright, so what's our total running time? We've got 21 n log n plus 21n plus 34n plus 1. Alright, so that's 21 n log n plus 25n plus 1. Total running time. Alright, so what's the asymptotic running time? Well, let's again look at our highest order of n for each term. This one's n to the 0, this one's n to the 1, this one we've got n to the 1 times log of n. So is n log n greater a higher order term or a lower order term when compared to n to the first power? Well, to answer that, well, we know they both have an n. So one way to think about that is, how does n log n compare to 1? Well, your plot of log n will typically look like something like this. Probably a little more gradual than that. The point is, here's 1, and for certain values of n, log n will be greater than 1. And since we care about large values of n log n will be greater than n. So our highest order term is n log n, so we're going to take the guess here that this thing is big O of n log n. And just as a point of notation, I did this on the previous slide and didn't explain it, but log n will be my notation for log base 2 of n, just so I don't have to type out when I type things out, and so I don't have to write out log base 2 every time. So if I have log, that's going to be log base 10, and as you know, like natural log is like log base e. All those are pretty similar, just slightly different notation. They're all going to be logarithmic though. So big O of n log n. Alright, like I promised, we'll do this one two different ways. We'll do it with the intermediate step, and then we'll do it once without the intermediate step. So here, let me go ahead and do it without the intermediate step, since we haven't seen that one as frequently on this in my slides here, my videos here. So what are we trying to do? We're trying to say that 21 n log n plus 25n plus 1 is less than or equal to n log n times some constant c for all values of n greater than or equal to n naught. And we're trying to find c and n naught. Alright, so a common way to do this is to divide everything by the highest order term. So that's going to cancel it out from here, cancel out an n here, and cancel it out here. So what we're left with is 21 plus 25 over log n plus 1 over n log n is less than or equal to some constant for all values of n greater than or equal to n naught. Alright, well, what I like to do when I've got my value n here in the denominator, because remember, we don't want a final value for c that includes n. It turns out here that you can come up with a value of c that's greater than the left-hand side, even though the left-hand side includes n, because n is in a denominator, which means these two terms are continually shrinking over time, which means it's not growing, which means we don't have to continually get a larger and larger value of c. It's still better to get rid of n, and in fact I'll require you to get rid of n. Never give me a value of c with n in it. So we'll just go to each one of these terms and we'll try to simplify it a little bit. So for example, 25 over log n, let's just try to cancel out the log n and have this value be sort of less than or equal to 1. So we have to figure out a value for n for which 25 over log n is less than or equal to 1. So for example, if I say that n is 2 to the 25th power, I'm going to have 25 over log of 2 to the 25th power. And you can't pick values for n except for when you're trying to get it out of the denominator like this, and I'll show you why here. A nice property of logarithms is that if you have an exponent here, you can just bring it out front. So we can say that 25 over 25 log 2, the 25's cancel out, and we've got 1 over log base 2 of 2. Log base 2 of 2 is 1, so this thing is 1. So whenever you pick a value for n, when you're doing an asymptotic proof, you have to say, well, what happens if n becomes bigger? So that's always what you're trying to guard against, is what happens when n becomes bigger. Which would mean I, for example, could put a 26 here. So if I put a 26 here, that's like having a 26 here, which means 25 over 26, that's a number less than 1. So I'd have a number less than 1 times 1, because 1 over log base 2 is 1, which means this thing becomes something less than 1. So as n gets bigger here, the point is as n gets bigger here, it's going to continually get less and less than 1. So we don't have to worry about just sort of arbitrarily picking a value for n and using that to solve for a good value. So what does this mean? It means that if I want to plug in a 1 here, I can only do that for values of n greater than or equal to 2 to the 25th. And 2 to the 25th power may be a big number, but it doesn't matter, because we're still going to end up with a constant value for c. So this is just one way to do the math to make it easy to find a constant value for c. So I think what I'll do is I'll duplicate this slide and then clear it. That way I still have the slide saved, and it'll be in the lecture slides on the course website, but that way I have more space and I can give myself more space. Alright, so I duplicated the slide, and we'll pick up where we were here. So what we had was 21 plus, so I'm looking at this equation here, so we'll say 21 plus 1 plus 1 over n log n is less than or equal to some constant for all values of n greater than or equal to n naught. And we know that n naught so far has to be at least 25 for that inequality on the left hand side to work. Alright, well let's look at our final term here. We have to replace 1 over n log n with something, so 1 over n log n, and let's just replace it with 1 also. And it doesn't have to be 1, you could pick any constant you want to replace it with there, but 1 is sort of an easier thing to do. Oh, I made a mistake here, didn't I? I said that n has to be greater than or equal to 2 to the 25th power, not to 25. So that's 2 to the 25th power. Sorry. I knew something didn't look quite right there. Alright, well, I know that log of 1 is 0, so we want to stay away from that. So we need n here to be at least greater than 1. Sorry, not greater than or equal to, but strictly greater than 1. Otherwise we'll have a 0 in the denominator, and that's some math we don't want to deal with. And we know that log of 2 is going to be 1, so really this thing would be best if it's greater than or equal to 2. Because if I have a 2 here, that gives me, if I have n is equal to 2, I've got a 1 there, and I've got a 2 here, and sure, 1/2 is less than or equal to 1. So that won't be a problem. So here we say that n has to be greater than or equal to 2. Well, we've already got that n naught is 2 to the 25, so that one's going to be fine, and we can just replace 1. So we've got, so what we have is 21 plus 1 is less than or equal to c for all values of n. Now since we're done figuring out number values for n, for all values of n greater than or equal to 2 to the 25th power. So c can be 22 and n naught can be 2 to the 25th. This I will wholeheartedly agree to you if you think it's weird to have such a large value for n, because our inequality doesn't hold for a lot of different things that we would want to run our code on. But that's not the point. The point is, can you find a value for c and n naught? And now we've proved that the asymptotic running time of this is in fact big O of n log n. Alright, so for the next few slides I'm going to go through them pretty quickly. This is your exercise for today. So what I would recommend is going off to the course website, grabbing the exercise, running through those examples, and then I'll go pretty quickly through these in the next video.